just dropped down to 31.82%.
Okay.
Does that sound right? 31.82?
I don't know. I've spent no time on that. I've spent a lot of time trying to figure out how to help you guys learn this stuff. That's what you guys should be doing.
Franklin.
Okay.
And Robbie. Oh God, you guys figured it out.
I just want to 70. I wanted to say 70.
I'm sorry. You tried that?
No, but I've been trying to figure. I've been doing these problems for a while. I think I've tried. I don't know. It depends on how much stuff you guys want to do. I hope not, but
I really hope not.
it's up to you guys. It's up to whatever you guys want to do. We'll do. Except I won't do any pressure problems. But don't forget that pressure's a thing. I know.
You make sure you record it.
Huh? Yeah, thank you. It is recording. But thank you for I appreciate. There aren't any pressure problems on the review, but there will be a pressure problem on the exam. Okay. So you guys are here. There's more people coming. It's for real. This is a crew. Good, it's like I get to see all of you one more time. I know, but on Wednesday I don't really get to see you. You're like all wound up. Yeah.
Can you just give me 43.5% on this? I just want to pass.
Alright. Do you guys want to do a beam deflection or indeterminate problem, or do you? Okay.
Do you think we should?
I think we should do one of them.
Whatever one that you really do want that we should do.
Do you think? I kind of feel like we should do this one.
Whatever looks exactly like the questions on the test.
Yeah, the most similar to the test.
We'll do this. Okay, I brought tables. Do you guys want tables? Yeah. Okay. I will be. I printed out so many. Look at this stack of tables. So you have to return them tonight. So feel free and come get tables, and we'll do this problem. Okay.
Grab one, we can all share it. We can all point and be friendly.
Point and be friendly. Okay. You want tables? There's like both styles. Yeah. You can like spread them out a different way if you want. Cool. Cool.
You took it too? Yeah.
You just took it to get a better grade.
You're not going to be
Probably not.
Could you? If I get 100%.
Maybe. I might. There's two different kinds. Yeah. There's like. Yeah. Sometimes one is better and sometimes the other one's better.
A 90 exactly.
Oh yeah.
Oh, there. I see.
That's one style. And the other style, this one's just one page. The other style is more pages. Alright. Nice. At this rate, we're definitely here until 7. Alright. Okay, ready? Okay. How many reactions does this beam have? Huh? I am. Thank you so much for reminding me. I am recording. And my microphone was off, but I turned it on. So hopefully all is good. Okay. So how many reactions? 4. Technically 4. 3. How many equations do we have? 3. So it's indeterminate, right? Ultimately, we have CY. We have AY. We have a moment at A. And then we could have AX and we would only have some of the forces in the y, some of the forces in the x, and some of the moments about 1 point. 3 equations, so it's indeterminate to the first degree, right? So, what do I do? Yeah, get rid of one of the supports. Nice. And get rid of one that makes it easy. So, let's pretend this was simply supported. So just for a minute, this is a simply supported beam with a support right there. Get rid of that support, right? Because if you get rid of that support, then it's just a simply supported beam, right? So many people. We're doing an indeterminate problem. There's tables if you want tables. Okay, but it's not really that, but I just recommend you do that if you were given that problem. For this one, what is the go-to support to remove? C, yes. You could technically remove the moment at A, but I think that's harder. So you could remove the moment and turn it simply supported. But I think it's better to remove C. So then we're going to have two systems, right? So we remove the redundant support. And so that's CY. So then we draw a picture. I think it's worth drawing a picture. I really do. I know a lot of you guys don't agree with me on this, but so now that's something we could solve, right? Okay, so that's once we remove the redundant supports, we move C. But then we're going to have deflection, right? So this, like the elastic curve, is going to go something like this, right? And it's going to deflect some amount here at C, right? So then the next thing you do is you draw another picture of what kind of beam is this? What do we call this beam? It's a cantilevered beam. It's a cantilevered beam. That's just fun fact. So we draw another picture of a cantilever beam. Do I put that distributed load on this picture? No. What's the only thing I put on this picture? CY, right? And it's going to be a point load where we removed the support, right? So CY will go up. So then how would this beam deflect? It would go up, right? Oops, well, it would be curved, but whatever. So then this would be VC prime. But is there actually deflection at C? No. So we add VC plus VC prime equals 0, okay? So if you do that much, you'll get a lot of points. But the next thing you have to do is go to the tables. And for this problem, neither table is superior. They're both equally good. So you can just pick whichever one you want. Anyway, sometimes they're better, but we're not going to get into that. Okay, so go to the table. What tables do you guys like? I have tables. Do you like the 2-page tables? 2-page tables? All right, do they... Let me see. I'm going to see if it's perfect. Yeah, I'll go with that. Nope, I won't go with that. So these ones are harder. All right, so can anyone see why this table is harder? What would we have to do? This one right here. So we have a cantilever beam, and our only option is to have a distributed load across the whole length. So if you use that one with our problem, that's not what we're doing. Oh my goodness. Okay, so if you use that one with our beam, you would have to pretend like the beam ended here, and then calculate the slope here, and then do that whole slope times this length to get that deflection, okay? So in this case, the other beams are, or the other tables are superior, but this doesn't always, they're not always superior. So grab both and, I don't know. Does that make sense? So we don't want to do that because we would have to calculate the slope, everything. I'm lazy, and I know these tables really well, so I'm going to do this. All right, so because this table, see how this one has a distributed load over part of the beam. Cool? That's why we're going with this one. But it's not always the better choice. For here it is. Okay. So, all right, there's just way too many things open. Okay. Okay, this is what we're doing. Okay, so we're gonna put that here. Okay, does everybody have that table? So, this is something pointed out. So, we're lucky, right? Like our picture matches this picture exactly, right? However, if it didn't, you can flip things around and stuff like that, but that just comes with practice. So for this one, we're lucky, but you have to watch that and watch these rules and stuff. Then there's the rules. So you do have to pay attention. It's not just like grab and go. Okay, but if you pick a table, okay, so where are we calculating the deflection? At the, yeah, way at the end of the beam, right? So technically they call this big A and they call this big B. Okay, so what would our X equal if X starts here? Remember, X always is 0 at A. It's 0 here, and X gets bigger as you go across, okay? But you could technically flip that around. So what would our X equal?
L.
L, right. Good job. Perfect. So, can we use this equation? No, because that only works for X is less than A. Can we use this equation? That's slope. Remember, V primed equals slope. So you definitely don't want to use that equation. Can we use this equation right here? Yes.
Can you go over why x equals out?
Yes, so X is the place where we're taking the deflection. It cannot be stressed enough. X is where we are calculating deflection. Does that make sense? And we're calculating it all the way at the end. So X starts here at 0 and it's L over here. Cool? Good question. Okay, so we could use this equation, but is there, I guess it's the same, it's equally easy, right? So delta B is technically, that's also the deflection, but same thing. So we're actually going to use this one so we can practice what to do.
Why wouldn't we use the equation right below it?
Right below it, that's when X equals A. So that would be finding the deflection right here. And we don't care what the deflection is right there. Does that make sense?
Yeah.
So it's reading all these little details. Yep. Yes.
What is the difference between V and that little squiggly V?
V prime.
Yeah.
So this equals theta, the slope, remember? So V primed equals dV dx. Remember that from calculus? Yeah, so that's the slope. Does that help?
And then, what about the one with the other star, the sigma B?
That also is slope, but that they just write it different because it's the slope at the end of the beam. It's just like how they write this one with a delta sign instead of a V. It's just like how they do the max, kind of. Cool? Good questions. All right, so then the thing I recommend you do is write what all the variables equal. So Q equals what? W. Oh, you guys like this. It's no numbers. It's so much better, I think, someday. Oh, so much better. Q equals W. Okay, what is A equals what? L. Oh, you guys really love ones like this. A equals L. And what is... and X equals what? 2L. Nice. Okay. So then V is going to equal negative W times L cubed all over 24 EI times 4, use parentheses here, times 2L, especially if it was squared, then remember the 2 is also squared. This one's not squared, but that's a thing, minus A, which is L. I can't stress enough, like, write this stuff down. You'll get points for it, and it'll just make your life a lot easier, because it's easy to mess up this stuff, but if I know you're like, know what you're doing and you just messed up, you get more points, okay? So that's good to know. All right, so now this is the part you guys don't like, is simplifying it, I think, right?
All of it.
Yeah. WL cubed over 24 EI times, that's 8L minus L, so 7L. So then it's just 7WL to the 4th divided by 24 EI. Did I get it right?
Is that negative?
Yep, it's negative. Good job. All right, I did get it right. Okay, so that's our V. Now we need our V prime, right? So that's from the point load, okay? No load on there except for the point load. All right, so we go shopping for equations again. All right, did you find it?
For CY.
Yeah. Okay. Okay. So then we have this. Okay. So here we have two options. You guys see the two options? What? Which one? V? There's an easier option. Okay, but V is good. So you can definitely go with V. If you go with V, what's X going to equal? 2L. And then that would be squared. What's L going to equal? It's going to equal 2L. X is going to equal 2L. Remember what I said this one means? So remember, yeah, they always call this A and they call this B. So this is the deflection at B. Is that where we want our deflection? Yeah. Yes.
If you were to use that, just the B equation,
Yeah, that'd be totally fine.
would you just not use the negative? 'Cause
Right. Yep. We're going to make it positive because we know it's going to go up. Yep. Good job. Okay, does everyone see why? But you wouldn't be wrong if you used this one. You can totally do that. It's just a lot more work. Do you want me to do that? Or, okay, good. I really didn't want to do that. Okay. So, thank God. All right, so this one's going to be delta B, but it makes sense why I can use that, right? Cool. Okay, that's the key, is if we were calculating the deflection anywhere else, we couldn't use it. Okay, delta B equals P equals what? CY. That's right, I didn't do this. P equals CY and L equals 2L, my favorite. So then we plug that in. We have 2L cubed over 3EI. So that equals 8 times CY times L cubed over 3EI. Okay, so now what do I do? Yeah, add them, or yeah, you can add them, set them equal to each other, and solve, right? So, I see what's going on as I'm writing. This is updating. It's very confusing. Okay. So we have... Okay, let's do it the proper way. We have negative 7 WL to the 4th divided by 24 EI plus 8 CYL cubed all over 3 EI equals 0. And we solve for CY. Solve for CY. So you end up with 7 WL to the 4th all over 24 EI equals 8. 8 CYL cubed all over 3 EI. Okay, how comfortable are you with then? Okay, so then you have EIs in both denominators, right? So you can get rid of those. Right? Because you would multiply this one by EI. I'll do this in colors. So you would have EI times EI. Is that better? Demonstrating? Okay. Then you would bring in a different color, you would divide by L cubed, and you would divide by L cubed. So now that goes away, and that goes away, and this goes away. Yeah. I mean, you can do it however you want. Yeah. And then the 4 turns into just a 1. And then you're left with CY equals 7 WL over 24 times 3 over 8. I would actually rather have you guys leave it like this than but however, and then you could simplify it more. The 3 turns this into an 8. So then you get 7 WL over 64. We'll see why. Cool? So the key is just getting comfortable with the tables, which is its own thing. You have to really pay attention to the rules, and then knowing that you can like change you can change your beam so that A is A and B is E. Do you know what I'm saying? Like, do you remember this homework kind of? This is the unfortunate thing, yeah. This is the unfortunate thing about this finals. Usually it doesn't cover this many things, but yeah. But it'll be okay. 7.5 points, you got this. Use the tables
7.5 points.
for the deflection problem.
So that's like what? More than a quiz? 10%?
Less than a quiz. A quiz is 10 points.
Okay. So
Yeah. Yeah. Okay.
How many questions?
So that one's yes, John.
So this is for 7.5 points. How much is like?
Pressure's worth another 7.5 points. So I don't have any pressure problems on here, but don't forget to study pressure, okay? And mainly that's like knowing your way around your equation sheet, right? It's just going various up and down. And does everyone have an equation sheet? I brought extra. While you're studying for this, okay, I have extra, so either get them now or on your way out. And I'll try to, if you take them all, I'll try to print more. But use the equation sheet while you're studying, and like put stars on when we get to it. The things, they're right there. Under, yeah. Put star, okay, so don't forget about pressure, right? But that's like going up and down the pressure equation section, right? But you have 3 homework problems. We did 3 examples in class, so you've got plenty of examples.
So there's a beam problem that's 7.5. Some pressure that's going to be problems at 7.5.
Yep, and then there's
So there's 3 7.5.
there's 2 7.5 questions, a deflection or indeterminate problem, and a pressure problem are both 7.5. Then there's a problem like this that is broken down into short answer questions. So you don't have to do a whole beam deflection problem, but you have to know this, like how you would do parts of a beam deflection problem. And that's worth 10 points. It's like short, and there's a couple like true false questions and one just like Wiley quiz question. So that's 10 points. Okay.
Is that it?
Nope, so that's 25. And then the last 25.
50 points?
Yeah, it's 50, yeah.
I was confused.
Then the last 20. I wrote it lots of places. Right? So then the last 25 points are general combined loading. Okay. You got this. You got this, okay? Do you want to do this problem or do you want to do general combined loading? Both. Okay, that's fine. Okay. So we'll do this problem. Okay. Okay. Do you want to do this problem first? I don't think I have the solution. I might not have the solution to this problem. This could get interesting. Let's see. I've like made this. I've done these problems so many times in so many ways. I do. Oh my goodness, this review has become 40 pages long, but it's just because I've done it so many ways. Okay. All right, let's do this. That's not gonna work. Okay. All right. Oh, I guess I could have done that. Okay. Okay. Okay, so we're only gonna do H or K. How does that sound? But is H in tension or compression? I don't have my beam here. Compression, right? So you have this loads, they're symmetrical, they're pushing down on this beam. this beam would smile, right? It'd be a smiling beam. Happy beam, happy beam. So that means compression on the top and tension on the bottom, right? So is K in tension or compression? Tension. Nice. Okay. So, all right. I guess it's not symmetrical. P equals 25 kips. That means this equals 25 kips. Q equals 60 kips. All right. And then we have a reaction at AY and a reaction at EY. Do you guys feel comfortable solving for reactions? Cool. Good. So you would sum the moments, you get AY, you'd sum the forces in the Y, you get EY. So AY equals 46.25 kips, and EY equals, I don't even care, it turns out. I only did H. Okay, so EY equals minus all those and, the other thing. We're going to do H. So all we care about is what AY equals. Why do I only have to care about what AY equals if I'm going to do H? What's the next step? Cutting it, right? So if we cut it, this is an important thing here, is we're going to, so we're going to draw a free body diagram. And in this free body diagram, right on the edge, is H, okay? And we have our reaction here of 46.25 kips. And then following the sign convention, right? So there's always the sign convention. This is what we call positive beam sign convention, where if we're looking at the right side, the shear is negative and the moment is positive. And then remember on your homework, we also had an axial force, right? That was fun. It made a lot of you happy. And we have on the left side, we have V, M is negative, and we always draw the axial. But we don't have axial in this beam. But just to remind you, this is positive sign convention. So if we draw this, and we draw V going this way, and M going this way, what do I do? Yes.
Why do you know that it's positive sign convention for this one? Or just...
This is the rules of mechanics of materials. So remember how we always called tension positive, and then if we got a negative, it was in compression? It's the same thing here. We always call shear negative when we're looking at the right side, and then if it is actually going, if we get a negative number, that means it actually is going up. Does that help? So that's a good question. So it's just how we orient ourselves to knowing that we are in following, the rules of mechanics, kind of. Okay, good question. And this distance is 4 feet, and they told us that. So technically, we didn't even read the problem. We're not going to determine the principal stresses, because then we would have to do, what would we have to do to determine the principal stresses? Grind. We'd have to do Moore's circle. So you don't have to do that. We're just going to determine the normal and shear stresses at H.
Is there going to be any more circle?
No. Yeah, no. No, that'd be a big curveball. All right, so we're gonna determine the normal and shear stresses. All right, what are the equations for normal? What's the equation for beam bending? Sigma equals my over I. Nice. No.
What do you
No.
know when to use like the negative M1 over I?
Anytime, so in beams, you can do it. So like here, you can do it. Don't do it for general combined loading because it's too hard to keep track. So the way it works is you can do it for beam bending because it's easy to tell if your moment is positive or negative, and it's easy to tell if your Y is above or below the neutral axis. But with combined loading, there's like so much going on that to keep track of whether each of those is positive or negative, it's just way better to look at it. So you can still put a negative sign there, but I think you're getting to the point where you can kind of see it. But if you can't see it, put the negative sign and follow all the rules. Yeah, so it's like a tool, but the tool, yeah, you have to know how to use the tool, and it doesn't work well for general combined loading. It doesn't work at all. Okay, beam shear. What does that equal? It's not V over A. What is it? It's V times your favorite letter of the alphabet. Yes. Yeah. V times big Q over I times the thickness. Right? Okay. So those are our equations. So that means we need an M and a V at H, right? And so that's why we cut it. All right? All right. So now we solve for the M and the V. So we can do sum of the forces in the Y equals 0 equals 46.25 kips minus V. So V equals 46.25 kips. Can I draw the stress block now? Yeah. Which way does the arrow go on which face? Yeah. Right face goes down, right?
But if we got a negative number there, that means that we did it wrong, so it would be going
No.
down.
That would just mean that the right face goes up. Yeah, yeah. It means that, yeah, that it's not, yeah, this. Exactly. So, yep. So there we go. Okay, then we're going to sum moments. I always sum them about the cut because that's just what I do. So then we have positive M. Remember, forces go away at the place you're summing moments, but moments don't go away ever in the moment equation, right? Okay. So we have M, and then 46.25 times 4, is that going to be positive or negative? Negative. Right-hand rule, summing about the cut, we'd have minus 46.25 kips times 4 feet. So the moment equals 185 kip feet. Okay. Then they didn't give us I, but because this is symmetric, yes, there we go. Symmetric, we can do the purple area minus the green area, right? Okay, I'm not gonna make you calculate I on the exam. Okay, can I just write I? Is that okay? Yeah. It's, yeah, BH cubed over 12, and then you, yeah, but, yeah, okay, I'll do it. So this would be 12 times 20 cubed over 12 minus 12 minus 0.5. 20 minus 2 times 0.85 cubed
Thanks for giving me
over 12. All right. 2,126.9 inches to the fourth. Okay. So we can calculate something now, right? Which one can we calculate? Bending normal stress. So, bending normal stress is sigma equals my over I. All right, we know m, we know I. What's y?
Is the central. Okay.
Yeah, so it's the distance from the centroid to the place where we're calculating. So this is y in my over I. Okay, so YH is 3.5 inches. So Y equals 3.5 inches. Make sure you know what Y is. So sigma equals, if we use the negative sign, our moment was positive. So we have 185 kip times feet. Everything else is in inches, so times 12 inches per foot times y is 3.5 inches, all divided by I is 2,126.9 inches to the fourth. So sigma equals a negative 3.65 KSI. What does the negative mean? It's in compression. 3.65 KSI in compression. All right, now for the exciting part. Let's go Q. All right, so curve. All right. So now we'll calculate bending shear stress. All right. So now we have, this is tau equals V times Q over IT, and Q equals the sum of the Y bar I's times the A I's. And remember, YI is similar to D in the parallel axis theorem. Does that help? It's very different than the Y. Theorem's a hard word to spell. Glad you can't read it, because I don't know if that's how you spell it. All right, so yi in this equation is very different than y in the last equation, right? Okay, so we're going to have, so what do I do first? I'm calculating the shear stress at H. Draw a line. Yes, I draw a line through H, right? I draw a line through H. So this is where I am calculating the shear stress. And then this black line is the neutral axis. Okay, then I need two areas here, right? I need this top area and I need this section of the web. So if I have two areas, how many Y bars do I need? 2. Okay, so I need, where do they start? Both of them start from the same place, right? Yes, they start at the centroid. So the green, and they go to the centroid of the area. So this will be 1 Y bar. And this will be the other Y bar. Okay, so I did this kind of a convoluted way. I think this one you have to do kind of convoluted. Okay, so it turns out D equals 20 inches. YH equaled 3.5 inches. BF, that's the width of the flange at the top, is 12 inches. And TF is 0.85 inches. T-web is 0.5 inches. So, this one's annoying because I have to calculate the height here, right? Does that make sense? Or we could do it a different way. We could. Well, okay, so if it's 20 inches total, then all the way to the top is what? 10 inches? So, I'm gonna use a different color. So, centroid to top is 10 inches. So, then this height here is 10 inches minus 0.85 minus 3.5, and it comes out to 5.65 inches. All right. So, Q equals. So if I know that, what's Y bar for the green area? Yeah. So we have to go up the 3.5 it told us, and then halfway up the 5.65. So 3.5 plus 5.65 over 2. So that's Y bar for the green. And then the area is 5.65 times 0.5. And then we add Y bar to the top. We're going to do the way I normally like to do it, or not to the top, but to this black section. I'm going to go all the way to the top, and then what am I going to subtract? Just half of it, right? Because I want to go to the centroid of it. Yeah, so it's going to be all the way to the top minus 0.85 over 2. That's the other y bar. And that area is 0.85 times 12. So Q equals 115.5 inches cubed. All right, then you plug all of that in. What's my thickness? 0.5. Nice. So we get, and V is what we solved for here. So V is 46.25. Here, I'll move this up. Oh no, it wasn't where I wanted it. Okay, here we go. So V, forget we're not in our suite room where you guys can see everything. V is 46.25 kips. Q is 115.5 inches cubed. I is 2,126.9 inches to the fourth, and T is 0.5 inches. 5.02 KSI. Then you have to draw the stress block. So, B. For no, because remember that it comes in on the stress block. So that's just magnitude. And then, yeah. Okay, so bending's normal stress. Does it act along the length of the beam, or does it act up and down? Bending normal stress. There we go. Good job. Up and down. So remember, if we drew this, we would have the normal stress. We'd have compression on the top, right? Is this ringing a bell? And then we'd have tension on the bottom. So the arrow is the stress acts on the longitudinal axis. Make sense? That's good, important facts. All right. All right. So that means that our normal stress, we said it was in compression, is going to act here, right? Longitudinal axis. Nothing going on in the X and Y, or in the Y direction for stresses, normal stresses. All right, and that equaled 3.65 KSI. That equaled our sigma. Then our shear stress, we know that, remember we looked here, it'll be like that. So go down and up and match up the arrowheads and tails. And then you label it 5.02 KSI. And for beams, it's less important, but for general loading, you definitely have to put your axes. Cool? So that's that. And so that equals the shear stress. All right. Any questions about that? Beam bending, Q is the most annoying part, right? Y for my over I, centroid to where you're calculating the normal stress. Y and Q is centroid to the centroid of each area. Okay, and each area has its own Y. Okay. So then there's two problems. There's this one. And then there's the other one. Do you want the second one?
Which one's your favorite? Which one's most similar to the one on the exam?
I don't know, they both have their things. There's this one, and there's, I'm not gonna do all. This one, I guess, the important thing is that all of these are equivalent force systems. That's why we're like moving forces around and things like that. And you can move forces around because we're making moments, right? So like for this problem, has anyone tried this problem? No? Okay, this would be a good one for you guys to do on your own, but I'm gonna help you get started with it. So all of these are equivalent force systems, but for this one, if you have this P going around the shaft this way, and you have this P going around the shaft this way, and you're taking a moment about the shaft, what's the moment going to be? The sum of the moments. Nice. So moment is a force times a distance, right? So this would be P times that distance. This one would be P times this distance. Would this one be a positive moment or a negative moment? Positive. Would this one be a positive moment or a negative moment? Negative. So if you summed those moments around the shaft, they're not actually going to twist the shaft, right? The sum of the moments is 0. But what they are going to do, is remember, is they're going to put these forces, these on the shaft. So you can do this. This is Py, and this is Pz. And then you can go about and do all your things. Okay? So that's good. We'll do this other one, and then if you want, I'll come back to this one and at least maybe go through what the things are. Sound good? Okay, so here we go. All right. So we have this. So there's so many ways to do this. And that's what's hard, is because I keep trying to teach you guys a lot of ways, and in the process, I confuse you. Like it works way better. Like Zane, we're getting it with the dog bone. Gabe played with the dog bone today too, and it helped. Like, yeah. Like, but it's hard because each of you has to figure out your own way to do it, and I can try to like teach all the ways, but it's really hard because teaching you all the ways confuses you because there's not a system. So what my plan is going to be for today is I'm going to do it my way to start out with, and then I can show you some other ways, but I'll be around tomorrow afternoon if you want more help. Ryan will be around, Andrew will be around, but they really just take a lot of practice and seeing it. But today I spent so much time thinking about how could I make this any more clear and possibly less clear, but hopefully we'll see. So I think a good thing to do is to start, like it says, oh my god, all the points. We're not going to do all of them. Okay, I'm going to go through, I'll go through all the points. But I'm not going to do all the calculations. How does that sound? Okay? I'm going to go through all the points. And I'm going to do it this way. Okay, so we're going to start. We're going to start by looking at points A, and B. Okay? So, if we look at point A and B, ultimately what we're doing is we're cutting it here at A and B. And we're going to try to figure out what's going on there. What normal stresses and shear stresses are going on when we cut it here. Okay? So one way that helps do this, I think, is to draw a new set of axes at this point. So you have Z coming out there. Y is the vertical. And then X is coming out here. Okay? And then you probably won't have to do like A and B on the test, but for learning purposes, we're going to write point A and point B. And we're going to go through each load and figure out what it does at point A and point B and try to get some relationships going for you guys, okay? But before we can move on to that, we have to draw the axes for point A and point B. So when you're looking at point A, I'll give you a hint. Y goes up. What other axis and what direction does it go if I'm looking at point A? X. Yes. And which direction does it go? To the right. Nice. Okay? This is good. It's a lot of visualizing. Okay. If I'm looking at point B, again, Y goes up. What other axis is going to be on this picture? And Z goes to the left. Cool? All right. So, because I'm just like a systems person, systems work for me, I'm going to start with PX. So what does PX do? At point A or point B? What? Torsion. Nice. Awesome. So PX is going to twist around what axis? X, Y, or Z? Y, right? So torsion is always about the longitudinal axis, so that's Y for us. So we're going to have, this is going to be our torque, and it's going to equal PX times what? Yes, times Z2. So here's another thing I started thinking about. So we have a moment about Y, we have a force in the X direction, and a dimension in the Z direction. You can't have two X's in like, does that make sense? You have to have each one represented. A moment about Y, a force in the X, a distance in the Z, okay? And then you have this torque. Okay, so a torque, is that going to act at A or B or both, right? So you can think about moving this torque right down on top, and it's going to act at both. So PX causes a torque, a shear stress from torsion at both. TC over J. All right, and the torque at that location is PX times Z2. Then the last thing you should do before moving on is draw a stress block. I can't stress enough. I really wanted to come up with a different word, but that was the word. If you do this process and mess up everything else, all your math or whatever, you'll get so many points of the 25, okay? If you go through this process And just think about, yeah, so many. Way more than half credit. Yeah.
Alright.
Like if you go through all the forces and draw stress blocks as you go and write like where things are coming from, you'll get a lot of credit, okay? So, this is way more important than plugging stuff into your calculator. Okay, so now, what on point A, what face can I draw an arrow and what direction is it going? Top face, right? Because I moved this torque. The first face it runs into is the top face, right? And then the torque is spinning it round and round this way. So it's going to go to the right. All right, we're following this. So it's in the positive x direction. All right, and then for B, it's going to go the same way. Top face to the right. Sweet. All right. So now you know you need to know what C and J are. We'll get to that. What else does PX do? Yeah, some bending. Shear. Yeah, shear bending at A, and then what kind of bending? Yes, so those two are related, right? When they're related, okay, so at point A, so one way to see that is that A, remember we drew it in the y-x axis. So if we slide px down right on top of A, it's going to go like that, right? Okay, so what is the moment around that's causing that bending? So px times what equals y2? Nice. So we're going to have a moment around z that is px times y2. If we moved A and B up or down on that shaft, would the moment change? Yes, because y2 would change, right? So since y2 changes if we go up or down, that's why we have the shear bending stress at A. So if you have a moment that changes, then you're going to have a shear bending. We use a different color. So this is still from PX. At A, you're going to have tau equals VQ over IT. But at B, these two are related. Sigma equals MY over I. Okay, what does V equal? PX, yeah. V just equals PX. What does M equal? PX times Y2. All right, so then, what's the next step we do before we move on? Yep, we make a square. Okay, we're going to do the shear first. Which face? Which direction? Top face? Right or left? Right. So PX is going in the positive x direction, right? This is our positive x. So when we slide it down, it's going to go in the positive x direction here. So we're going to have px to the right. Okay, here's a question. Now we have normal bending stress. Is it going to go in the y direction or the z direction? At B. It's in compression, right? It's in compression? It's in compression, okay? Y-axis or z-axis? Y, right? The longitudinal axis. So bending stress goes in the longitudinal axis. So we have just like before. Yeah, I'm not going to draw the picture again. Bending stress is longitudinal axis. So we would have compression and Y. Cool? All right. Does PX do anything else at A and B? Does not. Okay. So then we move on to PY. It's a very arduous process. PY. All right, what does PY do? Does a couple of things. Huh? What? Yeah, at which one? A. Nice. Said that with confidence. Compression or tension? Compression, right? So PY. Oh yeah, I brought the dog bone. Okay, PY. We slide it over, so it's going to like pull on something up here, right? It's pulling this way. So it's pulling this way, and it's bending. This is even worse room for, yeah. So that means, so if we pull it this way, PY is gonna like bend this thing down, which is then gonna bend this thing down, and A is going to be in compression. Good job. Does everyone kind of see that? Okay, so what's the moment going to be? PY times what? PY times, yes. PY times Z2 is going to be what makes it bend that way. So we have PY causes sigma equals my over I, and the m equals PY times Z2. Cool? All right. And which direction does it act? X or Y? Y. And it's compression. Always longitudinal. Okay. What else does PY do? Doesn't. So, good. So, and Y. So, this moment is PY times Z2. So, does that moment change along the length of this? It doesn't. It's always going to be whether we cut it here, we cut it here, we cut it here, we cut it here, we cut it here. It's the moment is going to equal PY times Z2. Glad you said that. But because we took this moment, that means we can take and move our PY to here. What is PY doing there? First thing you learned. Right? It's just a compressive normal force, right? F over A. Remembering? Yeah? So it's just like we're squishing it. Squishing it straight down. So now we're back to PY. And is that going to be at A or B or both? Because that's uniform. Sigma equals F over A. Remember, that's a uniform stress. So if I were you, I would take like a pink pen or some fun colored pen, and I'd take this equation sheet and I'd put a star by that normal stress equation right under axial stress, because that's one of the things that could be in these combined loading problems. I would put a star next to the torsion equation, right? TC over J. Then I'd flip it over and put a star next to the beam shear, tau equals VQ over IT, and the beam bending, MY over I. Now, unfortunately, it's not overly organized because Q for a circular section is in beam shear. I think most of the other things you need, I for a solid is at the top of the page. A is, so some of the other stuff you need, you kind of have to look for. J is with torsion. So anyways, but know those sections. Cool? All right, so let's keep going. Okay, so we found out that Py makes an axial stress, an axial normal stress. F equals Py. What does the stress block for that look like? Does it look just like the other compression ones I did? Right? Longitudinal axis. So I'm going to give you, like, because we're not doing pressure, you won't have any normal stresses that aren't in the longitudinal axis, okay? So axial is your normal stress you'll be working with. That's always in the longitudinal axis. And bending normal is always in the longitudinal axis. So you won't have any that go across the beam because that would be pressure, okay? All right, so does Py do anything else? No. So we can move on to PZ. Oh my goodness. All right. PZ, what color? We're gonna do bright blue. PZ, what does it do? At A and B. Yeah. So bending normal at A, nice. So it's going to be a moment about X, and it's going to be PZ times what to get to A? So it's Y2, right? So we're cutting it here. We're going to take PZ times Y2, perpendicular distance, right? And we're going to get a moment around X. So that's going to be PZ times Y2. Will that moment change if we move A or B up or down? It will. So what does that mean we're also going to have? What two go together? Like up here. Shear and bending normal, right? So if A is going to have sigma equals my over I, and the moment equals PZ times Y2, and it's a changing moment, then B, which is 90 degrees away, is going to have shear equals VQ over IT. Cool? So PZ can't cause a bending normal and a shear bending at the same place. Does that make sense? It's one or the other. So on your sheet, another thing that's worth noting is that when looking at one plane, that's what we're doing right now, like A and B. So like A and B. you would have sigma equals F over A, and shear equals TC over J is the same at both. Right? And then sigma equals my over I if m changes along the length. If you're looking at sigma A, then tau B equals VQ over IT exists. Okay? And vice versa. This could be A and this could be B. Does that make sense? So those two things are related. But if sigma is constant along the length, there's no tau equals VQ over IT with that force. Does that kind of make sense? It's words. I don't know, hopefully. All right. Okay, so m pz times y, it's changing. So then it's normal. We have a shear. Normal, it's in compression. Always the longitudinal axis.
So that was at C or D, would it be?
Yeah, so C and D, everything would be in the Z direction. Yeah. Okay, and then shear, we would have PZ. So we have the Z-axis right there. It would be, move it down. Helpful? Okay. Oh yeah, no, that was good. Okay, cool. All right, so, yeah. So then we look, yeah, and it goes in the positive Z direction. So it goes to the left. All right. Yes. So that, the only way I know how to do it is to like think about pulling on that pipe, right? So if you pull on the pipe where it is, it's gonna bend the end of that pipe down, right? Which is then going to bend this vertical pipe this way. Does that kind of make sense? Yes, sure. I need Westpaw to start making
Only
these.
way I thought about it is if it's bending, that Z bends it this way, it becomes a smiley face, and that A point is right here, so that A point's in compression. So then, since it's a smiley face, the top is in compression, bottom's in tension. So A is in compression, so that's why it's in the axial direction.
So it's like trying to picture what's gonna happen. Very good, yes, very good. It's good, it's good. Because it's just picturing how this will deform. So I'm gonna make, so this, like if you're pulling on, which one were we talking, PZ? So it's gonna pull it out, right? Which is then going to pull it out here. And so then if we have a moment, it's going to bend it, right? It's going to bend it so that it bends out like that. Does my green colors help a little bit? Because it's gonna like pull it that way. It would make more sense to like redraw it and it's gonna like start bending like that kind of. Does that make sense? Does that make better sense? And then the outside would be in tension. So it'd be like that. Does that help? A little bit? So it's just kind of trying to picture when you pull here, how does that affect this? Playing with dog bone did seem to help. Yeah. Okay. Do you want to do C and D? Max does not. It's okay. Do you want to do the other problem? Do you want to do anything else?
Is there by any chance? Yeah,
Huh.
could you scroll down so
Oh yeah.
is there by any chance you have a video of yourself finishing the
Yeah, do I have
or the other one?
there's videos of me doing both or both of those problems.
Post those.
They are posted. They're on YouTube. They've been posted for a long time.
There yet. I'm still working on the
Oh.
stuff that I haven't learned.
Oh
I'll get
yeah.
there in a sec.
They're on YouTube. Yeah.
Yeah, I'm just.
They're like from years ago, so they're like slightly different than the way I presented them tonight, which might be good.
Where's the link to the YouTube?
It's in the examples tab of D2L, and it's the first thing in that examples tab, but these problems are way down at the bottom in examples. Yeah. But I'm happy, like, if other people want to stick around and want more help, I will stick around.
I have one question.
Yes. Yeah.
Is V, would that just be PZ?
Huh?
Would V for the PZ, like formulas?
Yeah.
Would V
Oh.
equal PZ? So I don't know the term.
Yeah. So anytime, yes. So this, yeah. So that's a good question. Yes. V equals the force we're using.
Okay.
And like here, F equaled PY because, yeah. So yeah, good question. Yep. Yeah. And here V equaled PX because it came
Yes,
from
yeah,
PX.
that's what I was asking about.
Yep. Yeah, that's good.
Right,
Yeah.
so I just wanted to clarify.
Yep. Good question. Helpful?
Very helpful.
Okay, good. Don't forget about pressure.
You should bring that.
The dog. Okay, well, I'll bring the dog
Or
bone
is
for
that
you.
like cheating?
No, you can use the dog bone. No.
I'm gonna
I
fuck
wish more people would try to use the dog bone. It helped you a lot. That's if I could just work with you all one-on-one. Oh yeah, if I can have your deflection sheets back, that would be great. Or you can bring them, but it'd be better if I can have them. Helpful? Elijah?
You said we get these both tomorrow or Wednesday?
Huh?
We get both.
Yeah.
so close to an A.
Yeah.
92 is an A.
Dude, just be grateful, man.
92's in it.
Be grateful that you passed.
That's ridiculous.
Gabe?
Do we need to keep those or no? No?
I mean, if you really want to, you can. But I did send them to the testing center.
Oh, so it'll be attached to the exam?
Yeah, it should be. Maybe you should bring one though. I mean, it was my third email, and then they get.
Do we get one of these too? Or
Yeah, you get each. Yeah. So, okay.
Thank you.
Yeah. Nobody's gonna stay around? Oh yeah, take one of those and write on it. Use it while you study and write on it. Cool.
Are you doing more?
I mean, if you want, it's up to you guys.
You got it on YouTube.
I've
It's on YouTube.
Huh?
I'm good.
Is this gonna be in the videos posted?
yeah, I guess. Yeah.
On homework 13, Andrew tried to explain it to me, but he was kind of getting twisted around. How do you know, like, when you're doing problems like that between, like, when you should use the hoop stress or the longitudinal?
Oh, so it's based on, like, if you're looking for when it was a big deal, was when you're looking at a maximum stress. And remember, the hoop stress is the bigger of the two. It's twice as big as the. So that's when it matters.
Okay,
It's
so
like
when it
if you're
says look
looking
for the
for a
max
limiting, then you look for the bigger one. So if it's given, like, find the maximum pressure if this is like your yield stress and this is your factor of
So, like,
safety.
It said, like, what would it say?
Oh yeah.
If you're just using the longitudinal? It just
Then it would be like calculate the longitudinal stress. Yeah. And then you remember how to do strain. So remember, it's not just like 1 or like 1 over V. There's this equation. No problem. You have to use these equations for strain because it's 2D strain.
okay.
Remember remember these?
Yeah.
Okay.
Yeah.
So just
I'll have to
remember
look
them.
over. Are there more examples of those?
I just figured there aren't like a lot of examples, but I think if you just kind of revisit, don't like redo them all, but look at the examples and the homework. There's plenty of examples, I think, for you guys.
Alright.
Yeah, does that sound good?
Yeah.
But if not, come and talk to me
Okay.
if you have time.
Yeah, because you said you have.
I'm like all around to afternoon. I get my hair cut, remember?
Oh, yeah,
In the
that's
morning.
right.
And I'm like really excited about it.
Alright, thank you.
Yeah, okay. Do you guys want me to go through Talon other examples?